Hello, this is Jose Luis, and welcome to a new hands-on exercise on this series, Introduction to Parametric Modeling. In this one, what we're going to model is one of those one of those solar farms that you can find outside in the country, where you have a lot of solar panels that are oriented towards the sun, and that they rotate and they move over the day to be as perpendicular as possible to the sun. So what we have here is a surface that I'm going to hide for the sake of visualization. And then what we did was we created a bunch of panels, and each one of them has a particular rotation in the z-axis, but also a particular rotation on top of its own local axis, so that it follows the direction of a set of virtual rays that are pointing to the center of that panel, and they're always perpendicular as possible to the sun. So what that means is that as the sun might be changing directions over the course of the day, then each one of those panels could potentially move and reorient to be as perpendicular as possible and maximize the efficiency of how much energy they can draw from the sun. What we're going to learn in this exercise is a little bit of how can I say this? Looking at vectors in 3D space and figuring out how to create perpendicularity and how to figure out the right orientation for geometry generation and manipulation. So it's going to involve a little bit of 3D visualization of vectors or perpendicularities, etc. But if you are into computational geometry, I'm sure you're going to be able to handle this. So without further ado, let's get started. Wonderful. Let's get started. So before we start anything, I would like to set some context. What we're trying to do here is we're trying to mimic some kind of power plant of sorts, where we would have a lot of solar panels, and those solar panels are going to be actuated. They're going to have some kind of motors, so that across the day, as the sun keeps moving, the panels are going to orient themselves to always be as perpendicular to the sun as possible, so that they can capture as much energy from the sun. This exercise was inspired by a solar thermal energy plant that was actually built many years ago next to my hometown in Spain. This is not exactly what we're doing, because what this one does is that it takes the sun. The panels here are not electrovoltaic panels, they're just mirrors. And what they do is that they mirror the sun and they concentrate it here in this point. And therefore, this point becomes extremely hot. It boils water on a turbine, turbine. It boils the water of a turbine, and then the turbine produces electricity. Okay, so this is not exactly what we're doing. What we will be doing is just more like, imagine like a sunflower. What we want is like a panel that is always moving and is always orienting itself as close, as perpendicular as possible to the sun, to capture as much energy. And how are we going to do that? Well, at a basic level, what we're going to do is, by design, we're going to create a 2D grid of objects. Then we're going to elevate them a little bit from the ground, and then we might put some cones or not, just for visualization, as in this is standing on top of something. And then at some point, we will have a sun object, similar to the one that we had in the previous video. And we will perform calculations about the incidence that each one of the panels is receiving from the sun. And after that, what we want to do is we will have to come up with some way of orienting a rectangle that is going to be centered at these points that are elevated from the floor, from the ground. And the orientation of this rectangle should be as perpendicular as possible to the sun. So before we actually get into the problem of the orientation, let me build the basic infrastructure. Let me build the grid of points, etc., etc. And let's do that together, and then we can come back and we can break the problem of the orientation. Let's get started with that. Okay, so let's get started. For this one, we're going to go a little fancy, and instead of just like a flat 2D grid, we're going to work as if we were on top of some kind of undulating terrain. So I've made this surface on Rhino that I've done by lofting 3 curves, and I'm going to bring this surface into Grasshopper. And what I'm going to do is I'm going to click on the surface and I'm going to hide it so that we only get the pre-visualization here on, or actually I don't know, I want to do that so that we only get the pre-visualization in Grasshopper. And then what I'm going to do now is I'm going to take this surface and subdivide it into frames so that we get the subdivision of 10 units in each direction and 10 units in each direction, or less of them. All right. Now what I would like to do is I would like to create some kind of mast on top of this, as if it was a line of sorts or a cylinder. So what I could do is, in order to do that, I could just use the normal of the plane on top of the surface, but it turns out that when we're building things on terrains that are not even, we don't really build things inclined. We always keep the pure vertical against gravity. So in this case, keeping the normal would not make a lot of sense. So I'm just going to create on top of each one of the planes that I've created, I'm going to take the points, the centers of those planes. So I'm going to deconstruct the plane and get all of those points. And then what I'm going to do is I'm going to move those points up in the Z direction a controlled amount. So I'm going to move, these points here in the direction of Z. So that's going to be a vector in the Z direction, but an amount that I'm going to control. So that's going to be, for example, the height of these elements, for example. And I'm going to make that much smaller. So for example, 2 point something. And then maybe what I want to do is I want to join these two by lines. Maybe I can do something a little fancier later, but I can join the base point and the top point with lines. And you can see that now is one of those situations where I actually don't want to respect the curvature of the surface. I just want to keep the pure vertical here. All right. And it will be these points, the points that I've moved in the Z direction, it will be these points that I will want to use for the calculations of sun incidence. So let's take a look at that. So the first thing that I would like to do is I'm going to create a point and I'm going to move that point and I'm going to move it somewhere here, for example. And that point is going to be like the point for the sun. So I'm going to bring this point here, right click, set one point. And then after that, I'm going to calculate, I'm going to turn off this, and this, and this I'm going to keep. What I'm going to calculate is the incidence of the sun on top of each one of these points. So I'm going to do that with a vector between 2 points, and the first point is going to be the sun point, and the second point is going to be each one of those points that I have here. And just for visualization purposes, I'm going to drop here a vector display, which is going to visualize all these vectors from the sun, and the anchor point is going to be the sun itself. So I'm going to do that, and then I'm going to have this incidence. Okay, so let's take a look at that. Now I have the incidence of the sun, and what I want to do is I want to draw some rectangles or some planar rectangular surfaces on top of these points, center on them, so that I can orient this to the sun as perpendicular as possible. The idea is that for creating planar square surfaces, for example, if I go to freeform, there is no actual rectangular surface here. One of the easiest ways to do that is to actually go to curves and to go to rectangle. And then with this, we can create rectangles that are centered on top of our base plane, which means that, and then after that, what I can do is I can do a boundary surface so that that surface becomes an actual surface, a closed surface. So what I'm going to need, as you probably suspected already, is for each one of the rectangles that I want to place on top of these points, you see, for each one of the rectangles that I want to place on these points, this is not going to be good enough. I'm going to need to create some kind of plane where the plane actually has the orientation that is as perpendicular as possible to these vectors that I have here. And how am I going to do that? Let's take a closer look at that, and let's go back to the sketching board. One of the simpler techniques that I can use for generating these planes is going to be the following. Since I have a vector that is going from the sun into each one of the planes, what I can do is I can take that vector and I can flip it around and, for example, make it a vector that is pointing in this direction. And what I can do is I can generate a plane that is using that normal as the main direction of the plane. And then taking that plane, I will be able to generate the rectangle. We're going to try this. This is not the way we're going to go for the reasons that you will see very soon, but let's try this out. If we go to Rhino, what we can do is we can take these vectors, for example, that we have seen are the ones that are coming from the sun, and then we can just reverse them. We can flip them. So I'm going to take this, I'm going to go to vector, and I'm going to reverse these vectors. Okay? And as I do reverse those vectors and I visualize them, you can see that the vectors, which are still anchored in the sun, now they're facing the other way around. Well, so if instead of anchoring them in the sun, now I anchor them on top of the masts of these panels, then you can see that all the vectors are now pointing to the sun. Correct? And then it turns out that if I go to plane, there is a component that is able to generate a plane that is perpendicular to a vector. How convenient, right? How awesome is this? Shall we try this? Let's give this a try. So I'm going to place plane normal here. And then what's asking me for is the origin of the plane, which are going to be these points here, all the masts, okay? And then the C is going to be the normal, which I already have here as this. And then as I do that, I'm going to turn this off, and I'm going to turn this off, and you can see that I have a lot of planes that are kind of oriented towards the sun. Is that correct? And then as I plug those in here, you can see that now all these panels are now looking at, are they looking at the sun? So am I the sun? Yeah, they look like they're looking at me, right? Let me turn this on just to make sure. It pretty much looks like this is working. You can see how each one of the panels is facing directly towards the sun. Let me move the sun like really close to the ground to see if this is true. Let's see. Let's even bring this closer and closer. So you can see how now we have this kind of like concave sort of, yes. So this is great. Okay, so this is great. It's working. The panels are perpendicular to the sun, but can you see something not totally okay here? Is there something that we could improve? Give it yourself a minute to think about it. I'm going to give you some time. I need to improve my time passing kind of, you can pause the video and give it some thought. But otherwise, what I would like to point out is that the problem with the technique that we have used is that this component, the plane normal component, is a component that is able to generate a plane that is perpendicular to a vector. The problem is that the solution to that problem is infinite. The solution to the problem of a plane that is perpendicular to this vector, for example, might be this one, might be this plane here, but it's also this plane here, and it's also this plane here, and it's also this other plane here, and it's all the possible planes that you can have rotating a plane around a vector. So there's infinite solutions, and Grasshopper just chooses one arbitrarily with some kind of rule that we're not really sure of. And if we were on the field, typically this would not be a solution for us, because what happens typically is that these elements, what they have is they have a mast, and the way they can rotate is they can perform a rotation around the mast, and they can perform rotation perpendicularly to where the mast is. So this kind of solution is not going to work for us. And in order to get a solution that is more realistic with the real world, with two motors or two axes, one the vertical axis and the other one doing this, we're going to have to do a little bit of vector manipulation and vector analysis to fine-tune this solution. Are you ready for that? It's going to be super nice, super fun. Let's take a look. Let's take a closer look at the tip of one of these masts, or in other words, the center of where we're going to place the plane that is going to be the reference for the solar panel rectangles. If we take a closer look here, we have a few elements. The first element we have is the ray that is coming from the sun, is this vector that is telling us the direction of perpendicularity. And the other element that we have is that we know that the mast is pointing, is sticking upwards. So we have a vector that is somehow perpendicular to gravity. Okay? Now, what we want to do is, because the first angle that we want to find is the angle of rotation of the mast, like this, because this, we know that this is the first servo, one of the motors that the panel has. What we want to do is we want to figure out in a imaginary XY plane that was centered here at the tip of the mast. What we want to do is we need to find a vector that is perpendicular to the plane that is formed by these two vectors. If this vector, the perpendicular vector, and the sun vector, they both form a plane that we can find the perpendicularity for. And the perpendicular to that plane is going to be this one, and that's going to give us the angle that we need to rotate the mast to compensate, to approximate to that, to the sun incidence. And how are we going to do that? Well, we can actually create a plane, for example, that is going to be centered here at this point, and the main orientation of the plane might be this c vector that we have. The other orientation of the plane can be the vector, and then that plane that is containing the two vectors, the x and that is containing the origin, the normal vector, and the sun vector, that plane, the perpendicular to that plane, the normal, this one, is going to be the vector that we're looking for, is going to be the first vector that is going to serve us for the plane. Okay? So let's take a look at how to do that in Grasshopper. So we were here, and I'm going to remove like all this stuff that is not really working well for us. And I'm going to take the sun and I'm going to move it somewhere farther out here, okay? So that things are a little clearer. And I'm going to remind us that we have the vector that is pointing towards all these points, okay? Now, what I need to do is I need to be able to create a plane that it contains a plane that contains this vector, a c vector, and the vector of the sun. All right? So the way I'm going to do that is I am going to create a new plane. What is a new plane? I'm going to create a new plane. And how am I going to create this plane? The way I'm going to create this plane is by constructing the plane, okay? And then I'm going to use as the origin, I am going to use the points, the center points. Then the main x vector, as we discussed, is going to be a simple c vector that is going to stick up in the c direction. So I can just use a simple unitary z vector, no more complications. And then the y vector is going to be a vector that is going to be the sun vector. And then as we do that, you can see that these vectors these planes are now all oriented towards the sun. You can see that they include the vertical and that they also include the sun ray inside of them. And then you can see how their perpendiculars, their normals, are perpendicular to this incident. So let me deconstruct this plane so that I can get those normals and I can visualize those normals as well. So I'm going to display, I'm going to do vector display, and I'm going to display from these origins, I'm going to display the C vectors. And you can see how we are finding the vector that is perpendicular to the plane that is formed by the mast and by the sun rays. Okay, so we have those vectors ready, and then we need to figure out now what is the other vector that we need to find in this series of relationships. So let's go back to the drawing board. So as we have seen before, we now have this vector, the vector that I can't draw on. We now have this vector, the main vector x of the plane that will contain the panel. And now, but we now need to find the vector y that will be the secondary vector for that plane that will contain the panel. And that vector, the vector y, is going to be a vector that is going to be perpendicular to the two vectors that I already calculated. One, the one that I just calculated that is perpendicular to the sun plane, and the other one, which is going to be the sun incidence. So this vector is going to be perpendicular to that plane, and therefore what I need to do is I just need to create a secondary plane that is going to have two main axes. The main axis is going to be oriented towards the vector that I just generated before, and the other one is going to be oriented towards the sun. So as soon as I do that, then it's going to be very easy to understand that this vector, the perpendicular vector to this plane, is going to be the y vector for the panel that I am looking for. And once I have those two vectors, I can generate now a panel, a plane that is oriented perfectly towards that surface, towards the sun, sorry. So let's take a look at how to do that in Grasshopper now. So we said that we need to generate a plane that has the main direction x pointing towards the vector that we generated before, and the secondary direction y pointing towards the sun. So let's construct another plane. The origin is going to be the same point, the point at the tip. The x orientation is going to be the vectors that we just found before. So those are the normals here. So those are these vectors. And y is going to be the sun vectors. So where is the sun? Where is the sun? I forget where is the sun. The sun is here. Okay, so that's going to be this one here. And then if we do that, we can see that now we have all these planes. And just like before, what we had were vertical planes that were containing the mast and the sun. What we have now is this kind of horizontal planes that contain the sun ray, but at the same time have the perpendicularity that we calculated before. So let me, just in case, deconstruct that plane and discuss and show the vectors. So as you can see, I'm actually going to turn everything off. And now you can see we have the x vector and we have the y vectors. So can you see how this is super nice now? We have a family of two vectors per mast. One is the x vector and one is the y vector. And all of them are distributed equally and are going to be super useful to now create to now construct the final plane, which is going to be centered around the tips of the masts. The x vector is going to be the one that we just calculated here, and the y vector is going to be the one that we calculated here. And then I'm going to shut this down, and then we're going to see that now all the orientations are going to be consistent. So for example, where was this? Rectangle here. You can see how now, let's give this some, and now I can do boundary surface and then poof, just get this straight. All right. So how much nicer is this arrangement? So now you can see that all the planes are, you can see how they're basically rotating in one axis and then also inclining in the other axis. You see, as opposed to what we had before. Let me show you what we had before, which was planes that were created from a normal, and this was the center, and this was the sun, and then, so this was one alternative, the bad one, and then we used this to you see? So these are planes oriented like who knows how or why, whereas these are the ones that have like a consistent orientation now, which is super, super nice. So let's add a little bit of parameters here. So I'm going to add, for example, the size in the X direction, the size in the Y direction, and then you're going to, you remember how I have the expression, and this is going to be, for example, the dimension. This is going to be the dimension, and then this is going to be minus 0.5 times the dimension. This is going to be minus 0.5 times the dimension. This is going to be positive 5 times the dimension. This is going to be here, and I'm going to construct a domain. I'm going to construct a domain between these two, and then I'm going to copy and paste this for here, and these are the dimensions that I'm going to use for the panels. So this is going to be here and here, and these are also going to be here and here. And now I can say what is the height going to be, or what is the width going to be. And you can see that now all the panels are very nicely distributed in a consistent way to the sun. And let me hide this to make things a little more visible. And let me hide this as well. And let me hide this point as well. And now you can see that if I now move the sun, the orientation of all of them, can you see this one rotating? How nice is this one? How it's rotating. And now if I move down, you can see how it orients vertically, you see? Can you see the clear orientation of the two angles? And then you can see how it's looking. Each one of them is constantly looking at the sun and only rotating in each one of the two directions. Yoo-hoo! Alrighty. So I think this was the exercise that I wanted to do. Food for thought. You can add, for example, a cone in the mass to make it look a bit more nice. You can add thickness, and you could also, from this parametric definition, you could output numerical values for the radiance of the rotations so that you could feed those into a machine, and the machine would be connected to some servos and blah, 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 and would be actually moving these things in 2D or 3D. So that could be pretty interesting as well. I think with this, I'm done with this exercise. I hope this was fun. I hope the whole vector manipulation and the angles was not very confusing, but this kind of work is a lot of the work that we typically do when we're trying to analyze the orientations and the angles of things in 3D space. And long story short as well, I have worked here with creating planes that contain two vectors just for the sake of finding a perpendicular one to them. This operation would have been much easily done by doing an operation that is called the cross product of two vectors, because one of the properties of that operation is that the cross product of two vectors gives you a vector that is perpendicular to those two. So, but we didn't get into that. We're not going to get into that in this series. So I just decided to keep it easier with planes, for example. And that's it. I think, yes, that's going to be it for this exercise. Thank you very much. Thank you for staying here. If you learned something, or if you want to show some gratitude, feel free to like this video or subscribe to the channel, or any of those, or leave a comment, or extend this exercise to make it cooler, whatever you want to do, okay? It's up to you. So this is going to be the exercise, and yes, I'm not going to show that. Am I going to show that? Yes, I'm going to show that. All right, cool. Thank you very much and see you on the next video. Bye bye.